The next video I told you would have topics around the idea of reaction rate and what we can do to change or affect the reaction rate. What can we do to speed up a reaction? A little more sort of everyday examples. So just kind of a quick recap. Remember, there are three things that have to be true before a reaction will occur. Between, for example, as we had before, A and B to yield, say, C and D. Three things we said had to be true. One, you have to have A and B present. Two, A and B must collide with each other. And three, those collisions must have enough energy in them in order to break, form, change, rearrange the bonds that occur between A and B and allow C and D to form. So we need to have A and B present, they need to collide, and those collisions need to have enough energy. Now, what can we do then to make a reaction go faster? Well, we can add more particles. The first factor says you have to have A and B present. Well, the more A and B you put into the container, the more likely it is that they'll collide, and the more collisions, the faster the reaction rate. So by simply adding more concentration or using a greater concentration of a particular reactant or reactant, we can make the reaction go more quickly because there are more particles colliding. This could just mean using a higher molarity of acid or using a greater concentration of a particular solution or gas and being able to add more and more particles to the container or to whatever system you're working in, and to see that reaction rate go up simply by having more collisions. The second factor is temperature. Well, this is a pretty logical one. Typically, people think about warming things to make a reaction go more quickly, and that's true of basically every reaction out there. Some reactions like to be cooled, but even those require some energy to get going, that activation energy. And so when we warm reactions with heat gently, or perhaps in some cases very heated, we can find that by adding more energy, more particles will have enough energy to clear that activation energy hurdle. You'll have given more particles the energy to jump over that hurdle, be successful, and move on with their reaction to the product side. So when we add energy in the form of heat, the particles move more quickly, they move faster, and so there will be more collisions between them and more collisions that have enough energy for the reaction to happen. The easiest way I can explain with particles and the collisions and that sort of thing has to do with sort of putting cars on the streets of Bismarck. So if we adjust the temperature in a reaction, it's sort of like turning up the speed limit. If you could make every road in Bismarck have a speed limit 15 miles per hour faster than it is, well, if you suddenly said, oh, every 25-mile-an-hour zone is 40 and every 40-mile-an-hour zone is 55, it's dangerous, right? You can do that, and if suddenly we made those changes, there'd be all kinds of collisions because people would be going faster than they could safely handle the turns or handle the speed or the braking, and there'd be more collisions. So just by turning up the heat, just by moving those particles more quickly or allowing them to, there's going to be more collisions available for those A's and B's to bump into each other and make new products. So temperature is a pretty straightforward one. And again, we think about food spoiling as more of a biology experiment, but in the end, biology is based on a lot of chemistry. Those microbes that are digesting something or turning it from food that you like to rotten, spoiled food that you don't want, well, those are using chemical reactions. They're using enzymes, they're digesting proteins, and so forth. They're digesting things, and that's chemistry. So that's why we keep food in the fridge. If we want it to stay fresh, you're better off keeping it in the fridge and adjusting it from there. If you put food in the fridge, it's likely that the reactions that occur in the spoiling will be very, very slow, or perhaps they won't even happen at all and it'll last almost indefinitely. And again, think about trying to get over the activation energy hump when we talk about temperature and how it's impacting the rate of reaction. When we add energy, more particles will be able to clear that hurdle. The third factor that affects the reaction rate is the use of a catalyst. And again, a catalyst is a substance that reduces the size of that hill. If we simply use a catalyst, it'll shorten the hill and it'll make it more possible for the reactants to become products. More particles will have enough energy for the collision to be productive. Now this seems sort of a repetition of temperature. In the case of temperature, you're not changing the size of the hurdle, you're just raising everyone up a bit. By giving them more energy, you give them a better chance of getting over that hurdle. You don't change the height of the hurdle. As we talk about catalysts, you're not changing the amount of energy, you're actually lowering the size of the hurdle. So if you bring the hurdle height down, more and more of the atoms or molecules will be able to get over that hurdle and cause a reaction to occur, and fewer will be left behind because you've actually lowered the size of the required activation energy. Even if you don't change anything about the energy of the particles, okay, more of them will gradually be found above that line. And it's the difference in class between, if I want to raise all of your grades, an easy way would be to give everyone 50 bonus points. That wouldn't change what it takes to get an A or a B or a C, but by giving you 50 bonus points, more of you would move up into C, B, or even A range. As opposed to, if I decided I want more of you to have A's in my class, I wouldn't have to give you extra credit. I could just change the cutoff for an A from a 93% or a 92% down to an 85%, and suddenly there'd be more A's. Yay, everyone's happy. Except not really, because you haven't learned anything, right? So the difference between giving everybody bonus points to get more people to have A's versus lowering the standard or lowering the percentage to make sure more people get A's, there's a very big difference there. And if you can do both, boy, you can really make a reaction go quickly. And this just shows again what I was just saying, that when a catalyst is used, the reaction can take the lower energy route and occur, causing the reaction to happen more quickly and to get to the product side and to start going forward with maybe the next reaction in the chain. And finally, particle size. Well, not finally, I guess there's one more. But particle size is sort of similar to the idea with solutions. When you grind up a solute, it made more places for the solvent to come in and dissolve it. When we grind up a reactant or use a gas or a solution of a reactant instead of a solid piece, you're creating more surface area, and the more surface area there is, the more collisions there can be, the more places there is for a collision to occur on this side and this side and this side in terms of a reaction occurring. And so when you increase the surface area, there are more places for those collisions to occur, and that means the reaction will be faster. The nature of reactants. What the heck is this? We talked about nature with solutes and solvents, and we talked about polarity and non-polarity. Well, similar ideas here, I suppose, some of the same ideas, but the nature, more or less, speaks to the idea that when you have a reaction between ions, things like calcium and nitrate, sodium and chloride, silver, bromide, all these small ions, they're kind of like pre-packaged. They're pre-built and ready to go. So you can just stick them together however you see fit, and you get a reaction to occur. When the particles are small and simple, the reaction can be very fast. On the flip side, when we're working with large molecules, like even something as large as sugar, it takes a long time for those bonds to break. It takes a long time for the molecule to decide how it's going to recombine or reform new bonds after you've broken it. And these kind of reactions, because we have to rearrange things and kind of prepare the molecule to be reacted upon, it takes a lot longer for a molecular reaction to work. We can't change the fact that this is a big molecule and this is a small one. The little guy has an inherent advantage as far as the reaction going forward, without the help of a catalyst, for example. But when you've got a large molecule, it's going to be slow. When you've got a small particle, it's going to be fast. And there's nothing we can change about those things. But what we can do is adjust the other factors and cause the reaction to be fairly fast. When we do make adjustments, we get into something called Le Chatelier's principle, and that will be in a later video.